Wonderful. Okay, thanks so much. First of all, I want to say thanks to the organizers for putting together such a wonderful program and also for letting me participate remotely. This is incredibly fun. And I feel like I'm getting the best of both worlds, and the quality of execution is just really great. So thank you very much. So I'm going to talk about a line of research that we've been doing in my group as part of the bigger mission of understanding how we understand. So we communicate incredibly well with language. To a first approximation, a large proportion, maybe most of the sentences that you hear every day, that you produce every day, are new to you. And you, although we have misunderstandings occasionally, to a first approximation, we pretty much understand each other. And there are lots of ways this could go wrong. So for example, language is ambiguous. Language understanding takes place in noisy conditions. Our memory is constrained, and we don't know everything about each other, including we don't know exactly the expectations that our interlocutors will have about how we speak, how we interpret what we're. And despite all these things, we're extraordinarily have extraordinarily facility communicating, putting thoughts in each other's minds using language. And of course, in the broader context, we're interested in the scientific questions about how we do this, the knowledge and deployment of knowledge that underlies this communicative capability, which seems, as far as we can tell, to be unique in the animal kingdom. We also, of course, are interested in getting machines to do the same. What I'm going to talk about today is a line of work that tries to triangulate on this capacity, human or human-like linguistic knowledge and use, using a combination of linguistic theory, computational models, psychological experiments, and language data sets. And I think that's characteristic of a lot of the work that you heard about today and that you'll hear about tomorrow. And this is an instance of it. So, and the launching point I'm going to take is that I think, like so many other people, people in my group have been, and I have been very intrigued by the dramatic improvements that we've seen in natural language processing from deep learning. You've already seen examples earlier today. When I look at these, the behavior of these new language models, and keeping in mind that, just over a decade ago, N-gram models, which were obviously not learning grammar, were the best you could do when you were trying to actually deploy systems at any kind of scale in practical terms. Those were obviously not systems that had learned something like a natural language, but they were practically useful. Now the situation is much more interesting, and one's thoughts turn, if you're a linguist or a cognitive scientist of language, what are these models actually learning, and what's its relationship with what we think of scientifically as English? And so, I think maybe many people, like many people, have done this, started off looking at this anecdotally. Wearing my psycholinguist's hat, I started doing this by giving autoregressive language models contexts and sampling from their continuations and seeing how they work. So, for example, the girl who the newspaper is maybe an interesting context to look at. And if I randomly sample from a model that's already 5 years old, but is still interesting to look at, we get something that's sort of funny. The girl of the newspaper now calls his girlfriend has been really hateful. And that looks really weird, but actually, if you look at it from a grammatical lens, it's actually very impressive. So there's a newspaper, there's some key referent that's not in the sentence, but the newspaper calls a girl that person's girlfriend, and that girl has been really hateful. So that's actually grammatically great. Here's something that's more complex. The monologue that the actor in the movie industry likes made silent was being uploaded. And this looks like word salad, but actually it's totally successful. So the movie industry likes the actor made the monologue silent, and the monologue was being uploaded. This is a very impressive success. This doesn't always work. This is an ill-formed continuation, and then you get continuations that you can't even evaluate. But this is anecdotal. And so how do we make progress from here? Well, first of all, I want to point out that immediately some very interesting questions are raised. And I'd like to divide these into the category of technical questions, where we can ask, what generalizations do these models seem to be learning? That is, that if we think of the models as sort of, in some sense, interesting alien type creatures that have emerged on our planet that do something that looks sort of like languages that we speak, we want to actually understand those in a little more systematic way. And there's, of course, a huge amount of work in machine learning and natural language processing that does this. There's also interesting theoretical questions that bear on learnability. So, and this actually builds very much on the characterization that Charles gave in his last talk. The classic question of learnability is posed as follows. To a first approximation, children get purely positive input data. They don't get negative examples of, you can't say X. They get positive instances of, here, you could say X, just by listening and observing what the native speakers around them do. How well can these data alone deliver the right linguistic generalizations to what kind of learner? For example, a generic flexible learner without a strong hierarchical bias. And that characterization might actually be a decent match to some of the large neural language models that are being deployed today. And so we can imagine that, you know, some form of a model, imagine that sort of, and these are universal function approximation mechanisms. So in principle, they could represent something very close to what we think of as sort of linguistically interesting and probably right, but what do they actually do? And because we can train these models on data sets of a scale that is childhoods or human lifetimes or many human lifetimes of the data, we can start asking really great sort of proof by example of what generalizations could arise. But in order to do this, you need to take the right strategy. And so the strategy and argument that I'm going to present today are as follows. The strategy is that we're going to do what scientists do to understand a natural system, but we're going to do it on this artificial system that has emerged in the world, or these artificial systems. We're going to run controlled experiments on models, treating them as if they were subjects in a psycholinguistic experiment. So we're going to take as sort of experimental techniques that reveal and clarify the kinds of knowledge that are being deployed using purely behavioral paradigms. And I'm going to argue that standard deep learning models learn remarkably subtle features of human grammar from even just a childhood's worth of linguistic input. And that's just string inputs. And you don't even need non-linguistic grounding, which children have the additional benefit of. And I will be clear, the success of these models was very surprising to me. Going in, I was much more pessimistic, and I've been very positively impressed. And I hope to share some of that sort of positive interpretation with you and open it up to critique and discussion. However, I'll argue that from the point of view of capturing the real-time dynamics of how humans process language, these models still have a long way to go. They're not quantitatively aligned with human comprehension behavior, in particular, when expectations about grammatical structure are violated. And so the upshot will be that deep learning models offer scientific insights into learnability and powerful tools for expectation estimation, which is important instrumentally in all sorts of scientific questions. But they're not really a theoretical account of human language representation and processing. So to give you, I'm going to start by giving you the sort of big picture view of how we should think about language processing in humans, in particular in comprehension. The thing to recognize is that at any particular moment of comprehending language, you're probably in the middle of things, and you're in the middle of a whole bunch of things. You're usually not listening to the beginning or the end of a sentence. You're usually listening to the middle of a sentence. You might be listening to the middle of a word. You're certainly probably listening to the middle of a phrase. And so we actually need to take a very highly incrementalized view of language processing, and that turns out to be crucial to understanding the sort of the main body of evidence, empirical evidence in terms of human behavior and processing. So the general characterization would be that at any particular moment in time, you had some sort of recent context, maybe within the same sentence. You also had some broader context, which might be other discourse, even non-linguistic information. It turns out that you're constantly making predictions, and that those predictions actually modulate how you process the input that you accrue. Of course, this is happening in real time, so the current input gets integrated into the context, and then this keeps on going recursively. What I want to very briefly demonstrate is that it's not only are these predictions ubiquitous, it's actually sort of hard not to make them. So I'll give you partial sentences, and I think you'll find that the continuations naturally present themselves to your mind. And it's hard not to have that happen. So for example, and these involve many different information sources. So if I start with Jamie was clearly intimidated, then you probably think, and you probably didn't even need to wait, and reflect on it, that the next word is probably by, and then after by is the source of the intimidation. And that's interesting. The superficial statistics of language, for example, don't give you that, because most of the time the word form intimidated occurs it's the intimidatee, not the intimidator, that comes next. So there's actually like very rapid and effortless integration of the sort of broader syntactic context combined with lexical information and semantics. This also works with phonological knowledge. So in the context of Terriate N, you instantly think of things like apple, orange, ice cream cone. Whereas in the context of Terriate you naturally think of a very different set of objects, nectarine, banana, sandwich. So jointly semantic, syntactic, and phonological knowledge in this case are being integrated and deployed effortlessly. It's hard, in fact, not to deploy them. And this also touches on much more rich and sort of abstract and hard to really formalize characteristics of what we might call semantic and situational knowledge. So in the context of the children went outside too, of course, you all know that the word play is going to be next. In the context of the squirrel stored some nuts in the, you all know that statue is going to come next. No, you don't. You probably thought the word tree. You might have thought of the word ground, but most people actually in this context think of tree. And that illustrates something very interesting, which is that your inferences are not just purely derived from sort of facts about the world, because the most common place that a squirrel would store nuts is the ground, not a tree. But you thought of tree, and that's a complex story in and of itself that I won't really go into right now. I do want to emphasize that these expectations from diverse contextual cues affect human processing extremely quickly. Just to give you a brief illustration of this, one, and I know that Stan is very fond of reading, I'm extremely fond of reading. It's a wonderful model behavior for studying language empirically. So of course, your superficial, and in case you don't realize this, when you're reading, you're doing what are called saccadic eye movements. Your eyes sort of bounce around. They're not, even though you have subjective experience of a continual flow of input. So this is a little movie that I'm very fond of, which sort of illustrates this, this sort of the saccadic eye movement behavior. And what you'll see, hopefully this is going okay over Zoom, is that most of the time the eyes are more or less stationary, and then they jump. And you'll see that also they sometimes jump over words, okay? So this actually gives extremely nuanced and interesting signal that we can use to gain insight into how language processing unfolds over time, because it turns out that the movements of the eyes are very sensitive. They're exquisitely sensitive to linguistic context. A very simple way of demonstrating that is I'll give you here. So here's a context, and you can sort of think of what the next word is. This is a classic study by Rayner and Well, 25 years ago. The hikers slowly climbed up you probably think mountain. Every once in a while, somebody will think hillside. The nice thing about this word pair is that they dramatically differ in contextual probability, but they're matched for other characteristics like word length and frequency, which also we know affect reading behavior. So if you put these in context, and then you measure on average how people read them, you find a couple of really interesting things. First of all, the probability of the word in context actually affects whether your eyes even look at it. So you're over twice as likely just to not even look at the word mountain than you are at the word hillside, which is an illustration of how rapidly these expectations are deployed. It's also the case that if you do look at it, you actually spend less time reading the word mountain than you do hillside. And so this is just a simple illustration of the ubiquity and speed of these expectation deployments. Okay, how do we formalize this? It turns out that empirically, the best evidence that we have to date is if you want to understand the amount of work that is presented by a word in context to the human mind and brain, it turns out to be a very simple quantity and information theory, the surprisal of the word in its context. So surprisal is simply the log of the inverse conditional probability of the word. Okay. For example, if it's isolated sentence reading, I might use say the context is effectively the previous words in the sentence. And this is a very basic idea. It captures a very basic intuition. The more we expect an event, the easier it is to process. And as you saw before from reading, this is known. It's also been known for a long time in the neural response to language and understanding. So, for example, this is a study from Federmeyer and Kudus. The more predictable a noun in its context, the smaller the classic, what's called the N400 response. And there's a lot of interest in sort of trying to quantify this relationship as well more recently. But the fact that this is a graded relationship and it's probability sensitive has been known for a long time. And one thing that's really great is now we can start to think about the relationship between this kind of basic theory of how language understanding unfolds and what we can do in practice with deep learning models. And the practical fact of the matter is, if you have any language model that is a model that scores word probabilities in left contexts, if that language model captures syntactic structure, then we can get grammatical expectations. Now, it turns out that that actually is this shape relationship is actually pretty well empirically supported. So this is the shape of that relationship. Surprisal is this nonlinear transform of word probability. And we did work a number of years ago that we've updated more recently, and others have built on, shows that if you actually look at the quantitative relationship between how long people take to read a word in context and how predictable the word would be under a language model, well, you need a lot of data to do this because word probability is intrinsically correlated with word frequency. It's also correlated with word length, other variables that we know that affect reading. But if you have a very large data set, for example, then you can deconfound these with multiple regression techniques. And for example, generalized additive models, which allow us to recover curve shape in a very flexible way, show that actually the relationship between word probability and context and how long people will take to read a sentence that contains that word, that's a relationship that's basically linear over multiple orders of magnitude. So this is one of my favorite empirical results that I've been involved in here. So that's a really cool empirical demonstration. And it allows us to start talking about sort of things like milliseconds per bit or milliseconds per band. We can actually start to build quantitative theories of human language processing and relate them to computational models. Okay, so now what I'm going to do is I'm going to sort of make an argument that not only can we use that notion of log probability in context to look at human processing, but it actually turns out to be a very useful quantity for evaluating the capabilities and shortcomings of existing and new neural language models. So this is a rich line of work that we only started several years ago, but it's just sort of addictive and very fun, and we're finding that it's quite insight provoking. We have looked at a number of different kinds of models. I'm going to give you a tour of a couple of different examples of what we've done that I think you'll find sort of theoretically very interesting from a linguistic point of view. And one thing I'll emphasize is that we have some of the older models. So for example, this model that I showed you samples from is still actually a pretty interesting model to look at. It's no longer state of the art, but it has some pretty impressive behavior. And then we have, for example, GPT-3 here. And we also have models that are trained on far less data, just 1 million words, for example, but that we can do controlled experiments on whether they include a grammatical component, like recurrent neural network grammars that have a hierarchical syntactic structure to them that then is guided by a neural network versus a pure neural network model. So we can actually start to investigate like what role does syntax have, at least for these smaller data sets. And we have different kinds of model architectures. Just in terms of calibrating the data size, this is a training data set size. So about 90 million tokens is maybe something around human childhood's worth of linguistic experience. 9 to 10 times that is about a human lifetime's of linguistic experience. And you can see that now the biggest models are many times over that linguistic experience. But and we'll see that actually turns out to be sort of interesting to keep in mind. Okay, so I'm going to give you a quick warm-up exercise in terms of how to think about this. And it involves a very simple and very fundamental feature of natural language syntax, subordination. And I'm going to show it to you by example. First of all, here's a very simple sentence of English. You all immediately recognize it as a well-formed sentence. The doctor studied the textbook. I'm going to give that a green check because it's a well-formed sentence. Now, suppose that I add the word as to the beginning. As the doctor studied the textbook, period. That sentence now falls off a cliff, okay? So that you immediately recognize as an incomplete sentence. So I'm going to give it an X. This is a sentence that should be bad in some sense for a model that exhibits human-like generalization. Okay. Now here's another thing I could do. Instead of adding as at the beginning, I could add this second clause to the end. The doctor studied the textbook, comma, the nurse walked into the office. And you probably see that it's not as bad as the second sentence, but it's definitely not as good. It's a little weird. It's not as good as the first sentence. But interestingly, if I do both adding as at the beginning and the nurse walked into the office at the end, I get back to a great sentence. As the doctor studied the textbook, comma, the nurse walked into the office. That's great. And the reason is that as is what's called a subordinator, and it basically, from a structural point of view, it signals that the clause that comes next is not the main clause of the sentence. It's actually subordinated to the main clause. And so in order to complete the sentence, you have to actually end the subordinate clause and then do another clause. So this is it's an interesting abstract contingency relationship between a word and not any particular other word, but an abstract category. That is a relationship between between this word and an entire clause, like something that could be instantiated in an infinity of ways, but has to be there, okay? So now here's the way that I'm going to analyze whether any particular autoregressive model does or doesn't succeed in capturing this generalization. Okay, I'm going to split each of these examples into a context and a completion. And I'm going to be interested in the surprisal, the log probability, negative log probability of the completion given the context. And so this is that completion. I'm going to do this. So these are going to be the 4 completions. And now the idea here is that I should get different patterns of behavior when I manipulate the context by adding the word as, depending on the nature of the completion. So if I call the top 2 no matrix variance, because there's no subsequent what's called a matrix clause, then and the latter, the matrix variance, then what I should see here is that if I subtract the surprisal of the first from the second, I should get a positive number, because ending the sentence abruptly in this context should be more surprising than in this context. But I should get the reverse behavior in the latter pair. Okay, so what you should look for is and you're always going to see this in the rest of the talk, always look for a human-like processing signature is red bars up above 0 and blue bars down below 0. We're always going to be looking for that. Okay, and it turns out, so these are these 2 neural language models. This is the 90 million, or the 90 million word trained model. This is the 800 million word trained model. Both of their LSTMs. And you see actually that the relative success is it's sort of not, first of all, like the larger model actually isn't the one that does better. And B, neither of them sort of is more sensitive in the right way. The sensitivities are not quite right. So the penalty for not having a matrix clause after as is this red bar. And you can see that that's smaller than the penalty for not having an as when you do have a matrix clause. And so actually you sort of get the pattern quite wrong, although the qualitative existence of the contingency is present in this model. It's not really fully present in this model. Okay. And if we look, we now can look at very small models without syntax, and you see something very interesting. So this is a model that had only 1 million words of text to train on, but it had a syntactic structure that it learned. And this is actually, I would say even this model is not superhuman-like, but it's actually the least, it's the closest of the 4. So actually having structural representations can buy you things, at least at the small data scale, compared to the minimal contrast, same training data set, no syntactic structure. Okay, so these are relatively small models. Okay, so that's the warm-up exercise. Now I'm going to go to sort of the main event exercise, which is just very, very interesting and provocative, I think. So here's another perfectly well-formed sentence in English. I know what the lion devoured at sunrise. And I've illustrated it in a pretty unusual way if you're not a syntactician, which is I have this thing which is called a gap representation, which is, I'm just saying that there's nothing there. There's no word there. Okay, so the sentence is just, I know what the lion devoured at sunrise. And this is very structurally interesting for reasons that Luigi talked about actually at the very beginning. So the absence of a noun phrase after devoured is an important contingency relationship. This is what's called a filler gap dependency. What is the filler and devoured is the gap. And they're co-present, which makes this sentence okay. We'll call this the plus filler plus gap version of the sentence. Now, if I change either plus filler to minus filler or minus gap to plus gap to minus gap, I'll make the sentence bad. So for example, if I change what to that, I know that the lion devoured at sunrise. This is now an anomalous sentence. Devoured needs an object and I didn't give you one. So this feels weird. Likewise, if I left what as it is and I added an object, I know what the lion devoured the gazelle at sunrise. This is also anonymous because it's what doesn't really have a place to live in terms of the interpretation and the syntactic structure. But if I do both, I know that the lion devoured the gazelle at sunrise, I get a well-formed sentence again. Okay, so that's just like when the subordination example, we should have this sort of 2x2 contingency. If you're an experimentalist, you'll recognize this as an interaction pattern. Okay, so now let's actually look at the behavior of a neural language model in this context. What I want to emphasize here is that filler gap dependencies are a signature theoretically central feature of natural language grammar. Okay, so they've occupied a huge amount of attention and interest in the study of natural language syntax for decades, and they're a great interest in the study of acquisition as well, and in the study of the typology of languages of the world. What I'm going to show you now is models that don't have any syntactic guidance whatsoever. They're pure sequence models. And I'm going to show you their behavior in these cases. So this is a different example. Now it's I know that or what. The CEO showed the slides to the guests after lunch. And what I'm showing you here is I'm breaking in a sort of the psycholinguistic tradition, I'm breaking the sentence into regions, and I'm looking at the mean by word surprisal of something that's held constant as I vary whether there's a filler or not in the context. Okay, and this is the version of the sentence, the top two versions of the sentence when there's no gap. And it turns out that when there's a filler in the context, when the context had what, the model is actually more surprised when it hits slides, the slides. And that has a natural interpretation. The model actually expected the gap. And that actually matches well-known human reading time patterns for this kind of thing. Okay. We can, on the other hand, we can look at the converse case where I did have a gap. Now what's interesting is, of course, what happens right after the gap. And what we see is a reversal of the pattern. That when the context doesn't have a filler, the model is more surprised not to encounter an object. Showed should have an object. That's part of the facts about showed. And there's no object there. And the model is actually more surprised relative to the version where the filler is in the context. And so we have this opposite direction patterns. And we can actually just take the different scores of these surprisal profiles, and we get a very interpretable pattern that we're going to look for going forward, which is that so in the red lines version is the one without the gap. I'm sorry, I have the colors here reversed. So the red line here is when there's no gap, so I encounter the slides. And the blue line here is when I have a gap, so I skip over the slides and I just go to the guests. And having what in the context relative to that should make me more surprised not to have a gap and less surprised to have a gap. Okay, so look for that red line up, blue line down pattern. And what we see is in all three positions, subject that we tested, subject, object, and prepositional phrase, all of these can have gaps in English. All of the language models that we tested do have the effects, although you can see that the sort of the magnitude of the surprise effect it varies by model. And interestingly, it's not the case that the larger models are actually more robust in this respect. But I think we can say that like there's sort of the presence of the filler gap contingency. And of course, these are designed so n-gram models cannot possibly succeed, and they do not succeed. Okay, they're a chance. So that's an initial positive sign. But there are more characteristics of WH dependencies. So for example, this is an example of a simple WH dependency, but I can embed it. I can add said that your friend. And so now I have what's an additional level embedding. So I have added one additional level of embedding. And I can go to 2 levels of embedding, 3 levels, it's unbounded, okay? And so we can ask, well, what does the pattern look like as we increase the number of levels of embedding? And it turns out it's interesting. So you do get a certain amount of robustness. You can see here, once again, the red lines up, blue lines down pattern is there. However, here's an interesting thing. These are the transformer models, which are where all the hype's about. And they're trained on much more data. These are the LSTM models that are trained on less data. And you can actually see that the transformer models are the less robust of the two as embedding depth increases. Okay, so we're starting to see a story here of it's not just all big data always gets you to more human-like grammatical behavior or grammatical generalization behavior. It's a little more nuanced than that. Okay, now, like good experimentalists, we should address possible concerns and confounds. It's perfectly possible, for example, that the models might be learning a linear dependency between a filler and gap, not a hierarchical dependency. That is, when I have what preceding a particular region, I expect that there's got to be a gap corresponding to it somewhere. But that's not the way the filler gap dependencies work in human language. A filler must be appropriately above its gap in a structural relationship, for example, describable by C command under some syntactic theories. And so we want to test this, and we did. So here's an example of how we looked at this. So here's a context, the fact that the mayor knows who. So who is now deep inside the subject of the sentence. And so it should only be within this part of the sentence where I should actually have that contingency sensitivity between filler and gap. Not up here, because eventually I'll have to continue the sentence, give it a verb phrase. Okay, so there are 2 ways I could imagine continuing the sentence. Okay, so here's a version where the gap appears inside the subject, below the filler, and this should be okay. But if I switch it around, in both cases, and put the gap in the main clause, not inside the subject, it's the filler still precedes the gap, but it now no longer is appropriately below the gap. And so this should be not okay. And we're going to operationalize the prediction of not okay as there's no contingency sensitivity, or the contingency sensitivity is much attenuated relative to this sensitivity. Okay. And so I'm going to show you just sort of a brief overview of the predictions for this kind of human-like processing. Right. So here are three different versions of that context. So the fact that the mayor knows that versus who in the context. And we have a version of a continuation with no gap, a version of the continuation with a gap in the subject, and a version of the continuation with a gap in the main clause instead. And if we just look at the WH effect that we talked about here, what we should see is that we see a surprise effect here at the teller. So that should mean that you should have greater surprise here. And on the other hand, you should have little to no difference in surprise here, because this is the part of the sentence where you're no longer below the filler. Okay. When you have a gap, you want to look at this part of the sentence where you skip over the gap and see the surprise patterns. And in this case, we should have a robust reverse WH effect facilitation. And once again, little to no WH effect once you're back in the matrix clause. Okay, so here I'm going to show you graphs where there's inside the subject, and we should have big red up, big blue down, and inside the matrix clause where that pattern is much attenuated or absent. And that's actually exactly what we see. We see a robust pattern inside the subject, and we actually see that severe attenuation, often down to 0 for the matrix clause. Okay, so and this is once again surprising to me. These models actually seem to be sensitive to syntactic hierarchy in the deployment of filler gap contingencies. Okay, I'm just gonna, and so we've addressed this potential concern. I'm not gonna be able to get to the quantitative calibration today, but I will just mention sort of in a way, the most intriguing and provocative to me result that we found in this space, which has to do with what are called island constraints. So island constraints, for those of you who are less well-versed in syntax, are kinds of constraints on the set of possible filler gap dependencies. And in particular, in syntactic theory, and there are different versions of the kind of theory, but the general shared thing is that there are some kinds of phrases which do not allow linkages between, from outside to inside, a filler and a gap. So this relationship here, the gap is inside X would be not okay if it were an island, but something that's outside X would be okay. Okay, and island effects have been one of the number of candidates of sort of interesting learnability challenges for natural language that motivate potential domain-specific innate constraints. Because one thing to note is they're like a second-order thing to learn. So you sort of have to learn the filler gap dependency, and then you have to learn the restriction on the filler gap dependency from a point of view where you would have to learn those things. And furthermore, the idea is that the conditions under which islands would even possibly occur might be rare. So the sort of the support for probabilistic inference, learning from the absence of evidence, might be plausibly very low. And so it might just be a very hard thing to learn. So what we're going to show actually is that and I'm just going to show you one example here. That WH complement, that at least one kind of syntactic island actually attenuates the filler gap dependency as we've measured it in the same way that syntactic hierarchy manipulations do. So here's the example that's fine. I know what Alex said, your friend devoured at the party, perfectly fine filler gap. If I added that, it's still fine. I know what Alex said, that your friend devoured at the party. Might feel slightly more weird, but it's still pretty okay. But if I change that to whether, now it becomes really, really, really awkward. I know what Alex said, whether your friend devoured at the party. And the reason is that whether is generally considered to be an island introducer. And so that filler gap dependency is blocked. So we can go back to this pattern, and you've actually seen a version of this graph before. I'm just illustrating once again the sort of robust filler gap contingency. Red arrow up at the potential at the unfilled gap, at the filled gap, blue arrow down at the material after the gap when there's a gap there. That's the signature pattern of having learned the contingency. If I change the context so that intervenes, it doesn't really change that overall contingency. But if I change it to whether, now the contingency is almost entirely gone. Okay, and if we look at this across many models, this is exactly what we see. Is that the filler gap contingency is robust in control conditions, but it's not in island, but it disappears in island conditions. Now, once again, this seems like a very impressive success, but once again, we need to think about possible confounds. So we put on our experimental hat and think of alternative hypotheses. What if deep learning models have difficulty threading any type of expectation into a syntactic island? that would actually explain what we're doing and would have nothing to do necessarily with filler gap dependencies. So we test that by having a control. And the control has to do with expectations for gendered pronouns. And we use culturally or morphologically gendered subjects to set this up. So for example, the actress said that they insulted her friends. That's a match. And now mismatch is not going to be ungrammaticality. It's just going to be sort of more surprisingness. Okay. The actress said that they insulted his friends. That's more surprising. And we know actually from psycholinguistic data that that this would induce differential reading time patterns as well. And so this is sort of the control's control. This should definitely be a positive difference of surprisal. But now if I'm going to change that to whether, that sets up a syntactic island. So the question is going to be, do I see the same pattern or not? Okay. And once again, the question is here now we have a different kind of dependency. It's not a syntactic dependency. It's a co-reference dependency. Is that also blocked by islands or is it not? And so just to show you what this looks is the baseline condition, we get this robust mismatch effect. When we change that to whether, no change. We get the robust mismatch effect. Okay, so we get exactly the same behavior here. So that the islands, although they block this sensitivity to the filler gap contingency, they do not block sensitivity to gender pronoun expectations. I'm running a little bit late on time, and so I just want to say a couple of other things. So first of all, this is a different way of carving up that control. This is the data that you saw before. This, the fact that the gender expectations are not sensitive to islands is robust across models. I also want to, and so we've addressed the second potential concern. You can actually go and play with the kinds of tests that we've that I just described. So we actually have a website where a lot of these are uploaded. You can also write your own tests, test them on existing models. You can offer your own models into its syntaxgym.org. We have some visualization tools. I really encourage you to check it out. I'm actually going to skip the last part, which is about calibration to human data. Please go ahead and ask me about that in the question session if you like. But my main conclusions would be as follows. That standard deep learning models seem to learn remarkably subtle features of human grammar from a childhood worth of linguistics, but the model's predictions are not quantitatively aligned with human comprehension behavior, in particular when expectations about grammatical structure are violated. I didn't have time to go into that as extensively as I would have liked, but I'd remind you of the case of the subordination expectation violation case, where it seemed that none of the models fully got the pattern, where the biggest anomaly is actually falling off a cliff, only having a subordinate clause and not a main clause. None of the models, not even the grammar-based model, got that. So my high-level conclusion would be that deep learning models offer insights into learnability and a power-civic scientific tool whenever you need to estimate expectations in context, but they themselves are not a theoretical account of human language representation and processing. So thanks to my collaborators, my funders, and especially my lab, and to you all for listening. Thanks very much.